resolve the data this week. So today we'll meet at 3 o'clock, and it'll be a very brief lecture, and I'm sure in a very short period of time you're going to be able to finish the lab write-up. However, since you've already had the lab in your hand for this long, I'm not going to call it due until Wednesday morning. Okay? So we meet today at 3 o'clock for lab. I'll give about a half-an-hour lecture, that's all. Then you'll have plenty of time to get the lab all written up and turned in. Wednesday morning, yes?
Do you mean 2:30, or do you actually mean?
No, 3 o'clock.
Okay.
Yeah, I'm going to do something else for that first half hour. So now, a new topic, a whole new topic. We've been talking thermodynamics, and we've done, I think, a lot of fun stuff in those first 4 weeks of class. Our next topic, our next miniature class here is wave motion. And then we're going to take as practical examples both sound waves and light waves. But the key here is wave theory, which really is chapter 15. 16, 17, and 18 are pretty much practical examples of what's going on in chapter 15. Furthermore, the information in chapter 15 will be back to visit you when we get to chapter 34. So this is not a one-time only kind of a shot. This is going to be really important stuff. Take good notes, ask good questions. We're going to concentrate on this quite a bit. First off, what is a wave? Don't do this. A wave is an energy disturbance. Normally, to have a wave, you have to have an elastic medium. There's some distortion of the elastic medium. There's a restoring force, and the medium oscillates. So you usually find two things, a restoring force and an inertia. A restoring force and an inertia. And so we talk about waveforms, and we talk about things like, I often like to think about the string of a guitar. You stretch the string tight, you pluck the string, and a waveform develops. So, a wave pulse is a disturbance of finite size which propagates. Let's think about a stretched string. So if I'm thinking about a stretched string, do you guys play the guitar? Because I keep forgetting.
Yes, several people are.
One end of a guitar string is attached permanently. There's a device that supports it. There's another device that supports it up at the neck, and here we have a handle to change the tension in the string. And I think one of these is called the bridge, and the other one is called the nut. Is that correct? Which is which? This is the bridge?
Yes.
And that's the nut. Okay, so we're going to be thinking about what's going on between those two. And in that area, there's a string of linear mass density mu, that is kgs per meter. That's what we're going to think of as the linear mass density. And of course, there is a force, which we're going to simply call T, the tension in the string. So immediately you're going to notice, ladies and gentlemen, that we're going to start to reuse. Used to be T was temperature. Now it's going to be tension. And if temperature changes, we're going to have to come up with some fancy notation, because there's going to be a T for temperature and there's going to be a T for tension. There might even be a T for period. So be aware that you've got to remember the words, not the equations, not just memorize the equations. We're going to have to keep that in mind. So T is the tension or the restoring force that we're talking about. In the past, mu is the linear mass density. I will assert at this time and verify later that if I was to pluck that string, the speed with which the waveform would travel would simply be T over mu under the square root, like that. I'm just going to assert that. The first thing you might do is say, well, let's see if the units work out. T, tension, is a force, so that's in a unit probably newtons. And mu is the linear mass density, which is kgs per meter. And of course, a newton is a kg meter per second squared. And divide that we get meters squared per second squared. So the units inside of the radical would be meters squared per second squared. And once you take the square root, yes, at least it agrees units wise. That doesn't prove a thing. But it does not disprove it. How about that? It doesn't prove a thing, but it does not disprove it. Weird way to talk, isn't it? Okay. Oh, and by the way, there are two different types of waves that we're going to be talking about. The type of wave we're talking about here, where you have an oscillation along the string like that, is called a transverse wave. The reason we call it a transverse wave is because if you observe the motion not of the wave, but of the particles of the medium, you'll notice that the particles of the medium move straight up and down. The wave moves horizontally. The best example I can think of really would be take a piece of cork, throw it in the water, and watch a wave go by. If you observe the cork goes up and down. The wave travels horizontally, but the cork moves up and down. That's a transverse wave because the motion of the medium is transverse to the direction of propagation. Whereas another wave that I can't demonstrate so easily is a sound wave. Imagine the beautiful and melodious sound of my voice. What's going on is my vocal cords are oscillating fore and aft at a frequency of about 300 cycles per second, I know. I've measured them. And every time the vocal cords come forward like that, they compress a region of gas immediately in front of them. That region of gas is not stationary. It does move at a velocity of about 330 meters per second. So the vocal cords come forward, create a pressure pulse, and that pressure pulse leaves me and heads towards you. It spreads out into the room, only to be captured by your ears, funneled down to the tympanic membrane, which vibrates sympathetically. Immediately after going forward, the vocal cords retract, making a low pressure, forward, high pressure, back, low pressure, 300 times per second. That happens. So out of me, you're getting these pulses. If you were to somehow take one of those pins and color an air molecule, you would notice that the air molecule travels in the direction of propagation. As I'm talking to you and the wave pulse is moving through the room, you would see that the motion of the air molecules is longitudinal along the line of propagation. So there's two types of waveforms, that is a transverse wave and a longitudinal wave. Interestingly enough, I will always plot waves as transverse waves, and I'll tell you why in just a second. Go ahead.
Does that mean if we were to phase shift, if we were able to see the phase shift of all the molecules, if some would be red phase and some would be blue phase, or do they not move backwards? Do they just move forward? Oh,
they definitely, you're thinking in terms of like the terminology for the Doppler shift. In that terminology, then yes, it would be a red type shift or a blue type shift. But you wouldn't see that in sound, and we won't even use that terminology until we get into light. But the sentiment is correct. Where am I? Okay, so we have those two. Why am I going to plot everything as a transverse wave? Because if I was to, for example, make a sound in the room and we were to plot the pressure in the air as a function of displacement, draw a straight line from me to you, and then I'm plotting on the vertical axis, I'm plotting the air pressure, and the horizontal axis is the distance to you, then the plot would turn out to be transverse. Even a longitudinal wave can be plotted as a transverse wave. So transverse waves are so much more easily viewed that that's how I will always draw them. All right, so transverse and longitudinal waves. Now let's talk about the language of wave theory, because this is what's going to be important when doing your lab write-up this afternoon. If I was to plot a wave, and just for convenience I'll draw an easy to draw wave, but it does not have to be a perfect wave like that. Here is a picture of a wave, and I'm very fond of writing this, t equals 0. And that usually means, in my lingo, that means a snapshot at the beginning of the experiment. So here we have a wave which is actually traveling with a velocity v, but we have taken a photograph of it. So we freeze a moment in time. And this is how I indicate that. I just say t equals 0. That's the beginning moment in time. Now, if I measure, most conveniently, from wave crest to wave crest, what do we normally call that measurement? That's the wavelength, yes. So in this part of the class, I'm going to reserve lambda to always mean wavelength. By the way, checking your notes, I did just say most conveniently measured from wave crest to wave crest. That doesn't mean you have to measure it from wave crest to wave crest, does it? You can measure it from any point to any similar point, like from here, not to here, but there. That should also be lambda. The reason I used most conveniently was because there's no ambiguities when I state it in that fashion. Now let's imagine that we allow time to run. Let's imagine that we go right to this spot and notice that we are at the peak of the wave crest. And then we allow the wave to pass. We no longer hold it frozen, but we allow it to move. It's going to take a certain amount of time for one wavelength to pass. That is, we're observing this point right here. Right now we have maximum amplitude, and as you can imagine, as the wave goes by, the amplitude is going to sink to 0, go to a minimum, go back to 0, and back to the top again. That's how long it takes for one wavelength to pass. What do we call that? That's the period. So now, for us, t is also going to be period. There's a t for tension, and there's a t for period. And it's conventional to choose capital T for both of them. So it's going to be very important that you keep in mind which t we're talking about. Whether we're talking about a force or a time interval. Furthermore, frequency, which for our textbook, the author uses an F, but more conventionally we use the Greek letter nu. I tell you that because sometimes in the middle of lecture I forget what I'm doing, and instead of writing an F, I write a nu because that's very common. So frequency, how is it defined? That's exactly right. Did you hear what he said? No, you didn't. You're in the back of the room. It's 1 over the period. It's reciprocal period. That's exactly correct. And finally, then, now that we've talked about it, the velocity of the wave can easily be determined because velocity is distance traveled divided by the time it takes to travel that distance. Well, if you travel exactly one wavelength, lambda, it will take exactly one period, t, to travel that wavelength. Or, of course, nu times frequency, or, of course, nu times frequency. So there's a definition of velocity. So now we have defined wavelength, period, frequency, and the velocity of a wave at t equals 0. Back to this situation now. At t equals 0, then our waveform would look something like this. It is some sort of a function. It's an f of x. It's a function of x. And I like to think of it, remember that actually it is a two-dimensional thing. That is y of x and 0, t equals 0. Waveforms actually are two-dimensional things. They are a function of position and time. They vary in time, so they have actually two dimensions. But when we freeze time, t equals 0, I specifically indicate that with a 0 here, but that's the place for the time dimension. Now, what if we have a situation where a waveform is traveling, as we showed here? That at t equals 0, let's be very careful then. Let me redraw the picture. I'll use this board. I don't think we need this anymore. I'll use this board. I want to redraw the picture only to kind of declutter it just a little bit. So to begin with, I had a waveform like this, and just for convenience, y and x. It's not necessarily a harmonic wave, but it looks like one like that. So this is what it looks like at t equals 0. We'll allow it to move in the right-hand direction, so I'll put a velocity over here, v, in this direction, so that sometime in the very near future, let's say that it now looks like this. The interesting thing about waves is that they don't change their shape, they only change their position. So notice now we have now moved to a new position here, this space right in here. That is, let me get the right one here. That's this one here like that. This one is t equals t. What? T equals t. I use this notation to mean sometime in the future. T equals t, some arbitrary time in the future. So in the future it has moved some distance like that. What is that distance? Of course, this distance, which I might call x prime, is actually equal to vt. V is the speed of the wave, little t is the time t that has transpired since the beginning. I say that because now our new wave function, f, would look exactly like the old wave function if we did one thing, and that is to call the wave back that distance. Call the wave back that distance. If point by point on this wave you moved every point back exactly that amount, you would get back to the original wave function. I indicate that by saying x minus vt. That's y of x and t. So when it's time to talk about the wave function not frozen at the beginning of the experiment, but at any time in the future, then every place you had f of x before, wherever you had an x before, you just put it in its place, x minus vt. And that calls every point back the same amount. It calls every point on the new wave back exactly the amount that it has moved. So that gives you back. Now what if v is negative? You see here we're talking about a velocity which is positive, so let me make a note of that, positive. There's a velocity in the positive direction. What do you suppose happens if I'm talking about a wave that's moving not in the forward direction, but in the backwards direction? What happens?
Plus vt.
One thing and one thing only, that is you change the sign of this. So that would be f of x plus vt. You have, if the wave has moved backwards an amount vt, you pull everything forward the same amount. So that would be y of x and t. So the sign that you put here is always the opposite of the direction of travel. If the wave is moving in the positive direction, you put a negative sign here. If it's moving in the negative direction, then you put a positive sign there. So generally speaking, as a general statement, I will actually write f of x plus or minus vt equals y of x and t. And it's up to you to realize that the sign here is always opposite the sign of the velocity vector. If the velocity is in the positive direction, you choose the negative, and so on. Now, the reason I've drawn a harmonic wave here is because no matter how complicated a waveform gets, no matter how complicated the shape of a waveform, our old friend Fourier showed that any wave, any arbitrary wave, is nothing more than a superposition of harmonic waves. So we're always going to draw the nice simple representation and study only the harmonic waves. And then if things get complicated where you have, sawtooth waves, square waves, or even arbitrary waves, then you do a Fourier series and simply analyze the individual harmonic waves. What is a harmonic wave? I wrote this down on my paper. I thought, I wonder if they remember the notation. A harmonic wave, and you know what I wrote on my paper? I just wrote this. Somebody tell me what the words are. S-H-M.
Simple harmonic.
That's right, simple harmonic motion. A harmonic wave would be something like you would produce with simple harmonic motion. One of the greatest demonstrations I ever saw was a pendulum of low amplitude. As you know, that's simple harmonic motion. Take a pendulum and allow it to dribble sand on a moving conveyor belt. And as the pendulum goes back and forth like that, and the sand is distributed on moving, it makes a sine wave, a sinusoidal oscillation. Or, of course, another simple harmonic motion, which you probably saw in your Physics 4 class, is to take a disc, and you usually glue a ping pong ball onto the disc like this, and then you make it all spin in uniform circular motion, and then shine a light and show a shadow. And the shadow of the ping pong ball is simple harmonic motion, which can be translated in a moving system into a harmonic wave. In any case, in your math classes and in your early physics classes, you probably have seen many times the relationship between simple harmonic motion and sinusoidal oscillations. So, when we think sine wave or sinusoidal oscillation, we're going to think simple harmonic motion. The two of them are somehow connected together always. And when I use the term sinusoidal oscillation, sine wave or cosine wave, right? It just depends on where you put the axes. Those are identical waves. So, most of the time we can choose the axis. Oh, good. So, here's what we do. Let's draw a picture now. And I wrote, most of the time we can choose the axis so that we have in the y direction and in the x direction. Notice here, I'm going to put down here x down below like that. And then I'm going to show what I hope looks like a perfect cosine wave like that. Okay? So, of course, the distance from here to here is lambda. The height of the thing is amplitude A, like that. And these particular points, here, 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 and here, represent certain angles. On the top of this axis, I'm going to put theta. So the numbers that I write above are going to be angle numbers, and the numbers I write below will be actual physical measurements. And that is, at this point, of course, you're halfway through the cosine wave. When you've gone from here down to here, you're halfway through the cosine wave. There's the other half like that. So, of course, the angle that corresponds is pi, isn't it? As soon as I write pi, then the units that I'm thinking on theta must be what? That's correct, radians. So we've got radians up above there. If that's pi, then of course this is half pi. Did I write that in there? I didn't. This is then 2 pi. So this is half pi, this is 3 halves pi, pi, and 2 pi, and so on. I didn't write those two on the axes like that. Furthermore, if I want to think in terms not of angles, but in terms of length, would you agree with me that this point right here, this point x, is actually lambda over 2? That is half a wavelength. This, of course, is lambda. So, two ways of thinking about this thing. If you're looking at this sinusoidal oscillation, and we have chosen the axis to make this into a perfect cosine wave, then halfway through the oscillation could either be expressed in terms of angle or in terms of distance. And I like to think, when I think of distance, I like to think of it, what distance relative to a wavelength? There's the angle, there's the distance, and so on. So, for us, then, if I'm going to write down y of x and 0, because this is at t equals 0, then I would say, well, that is our f of x. And that is, notice here, a cosine, and I'm going to write the following thing. 2 pi times x over lambda. There is our angle. In other words, you choose any point you want. Like, let's take, for example, the halfway point. Then x is lambda over 2. If I put in lambda over 2, I end up cosine of pi. Oh yes, that is the correct angle. So, x over lambda is essentially what fraction of a wavelength have you traveled. This term, x over lambda, is what fraction of a wavelength. One full wavelength corresponds to 2 pi radians. So you multiply the fraction of the wavelength times 2 pi radians, and that gives you the correct angle at any point along this wave. Well, great! That means we are now ready to write down the completed waveform for what that is t equals t. What happens now? T equals t. What about sometime in the future? Well, this wave is moving in the positive direction like that. Hence, therefore, it's very, very simple. We can simply write down y of x and t is going to be, wherever you see an x, you put in x minus vt. Piece of cake. A cosine 2 pi times x minus vt over lambda. Good. Now we started with a waveform determined from a snapshot at t equals 0. Luckily, we had a very convenient and familiar waveform, a cosine waveform. Then, sometime in the future, to put the t right here, all you do is replace x with x minus vt, since we're moving forward. Well, great, let's figure out what that looks like. Let's clean it up a little bit. What we have now is a cosine 2 pi x over lambda minus 2 pi vt over lambda. But v is equal to lambda over t, so when we replace right there, we get y of x, and t is equal to a cosine. And now rewrite this just a little bit differently. 2 pi over lambda x minus 2 pi v, but that's lambda over t over lambda. And we get one more rewrite. Notice that the lambdas go away. Finally, a cosine 2 pi over lambda x minus 2 pi over t. And now we have the nice cleaned up version of our waveform, but it's conventional at this point to make this definition. 2 pi over lambda is called k, or it's simply referred to as the wave number, and 2 pi over t is omega, which is the so-called angular frequency. Keep in mind the units. Angular frequency is radians per second. Frequency is just per second. So I'm going to put that down over here. I'm going to make sure you remember rads per second. That's called angular frequency, when it's radians per second and not just per second. Yeah. So finally, our waveform now takes this very familiar shape that is y of x and t is equal to a cosine kx minus omega t. So that's the beginning of our standard waveform. We're going to use the cosine function very frequently in class when we're studying waveforms. Yes, I should be a little bit more careful. What if I was to write this? What would you guess just happened? Watch this. Y of x and t is equal to a cosine kx plus or minus omega t. What just happened? I allowed for what?
Reverse direction.
That's right, either direction. If it's going in the forward direction, I choose the negative sign. If it's going in the negative direction, I choose the positive sign. There's one last statement I would like to make, because you can't always choose the axes. Like, for example, imagine you're doing a pluck the guitar string type of experiment. And the way you're going to do the experiment is you're going to pluck the guitar string in a darkened room, camera sitting there, and you're going to take a flash picture of the waveform as it's moving on the guitar string. It's really hard to get everything lined up just perfect. So let's imagine that you pluck the guitar string and the axes, by the way, normally etched in the lens of the camera, gives you a waveform that looks like this. There's your picture. There's your snapshot. Oops, we're not lined up, are we? If we're not lined up, all we really have to do is to move this thing forward. I have chosen this to be a position, our author calls it X naught. So this angle, this corresponding angle would be phi naught. And phi naught, of course, is going to be 2 pi times x naught over lambda. And I know we're measuring in the backwards direction, but I'm just saying how big is the angle, not what direction is the angle. I'll take care of the direction in just a second. If I wanted to use this waveform for my experiment, all I have to do is to imagine that at t equals 0, I move all the data points forward exactly x naught or phi naught. So in the rare instance when the waveform is not lined up as a perfect cosine, we're going to assume that the cosine function is a little bit displaced half like that. So our equation now looks like this: y of x and t, a cosine kx plus or minus omega t plus phi naught. Phi naught represents the initial phase shift at t equals 0. Like I say, most of the time, you're going to be able to choose the axes and make phi naught 0. Sometimes, no. And when we write it with a plus sign here, we're imagining that the phase shift is, shall I call it, backwards relative to the y-axis. It's backed up that far, so you have to move it forward the same amount. So the sign here corresponds to something similar to the sign here. And I will reiterate most of the time that will be 0. Go ahead.
You always want to move it forward, even if it's closer?
No, I just want to have a standard way of drawing the picture. I'll always draw it this way. If you want to move it aft, you just put a negative sign there. That's all. All right, we're having such. Are we having fun yet? I think so. Okay, so now we've got the complete form of a wave function. Okay, the next thing we want to do, now that we have the wave function, and let me emphasize that by simply writing that down. Quote, wave function. The reason I do that is because now I want to change the story just a little bit. What I want to do is, as you know, when we did our first part of physics in Physics 4, we were kind of interested in descriptions of where things were. Then the second part of what was going on was how did they get there? The first part we call kinematics, the study of motion without regard to what causes the motion. Then after that, we were concerned with what causes the motion. And that's when Newton came into play. So what are we going to do? Newton's second law, that's what we're going to do. We're now going to consider how do these things happen. What's the reason for the motion? How do we describe it according to Newton's second law? Your favorite, right? Newton's second law just keeps coming back in physics. It's such a wonderful thing. So the wave equation is going to be a restatement of Newton's second law. And I'm going to draw a picture here which is analogous to a picture in your book. So don't try to draw this. I'll call the picture out in just a second. Don't try to draw this because the picture in the book is far more accurate than the picture I'm about to draw. But I need something on the board here. So the picture I'm going to draw, y, x, and I'm going to imagine a string with a relatively low amplitude, and the green line is going to represent the string like that. that. So there's just one little segment of the string. Perhaps this is a guitar string, we just plucked the guitar string, and here's one little segment here. And our author, I went and drew this, we're going to look at just this part of the string. So he goes like this, and he emphasizes it, makes it much, much larger, and it's going to look like this. And this represents dx, this represents dy, and as you know, there's going to be two tensions on each end of this little string segment. So there's a tension like this T here, and there's a tension like this T here. And before I put in any more details, let me get you to the right page. Did anybody find this in your book yet?
Yeah,
Page 505, thank you. This should be on page 505. It's a much better picture than the one I'm drawing, yes. So you're looking at figure 15.15. Our author does a lovely little job of drawing it there, and I'm doing the best I can. Now, why does this piece of string accelerate? There is clearly an acceleration. If time goes forward, this string is going to accelerate. In fact, it's at this point right now, if the wave is moving in this direction, if the wave is moving in the positive direction, which is normal for the way we draw things, then this thing is accelerating to a stop right here. And using the terminology of Newton's second law, there must be a force on it, right? But wait a minute, aren't the two tensions equal to each other? Yes, they are. Then how could this thing possibly be accelerated? The two tensions are equal in magnitude. How could this be accelerated? That's right, the direction. You're looking, if you look in the book, our author does a very fine job in here. He says this is angle theta, and this is angle theta plus d theta. The angles are not quite the same. The two tensions are not oppositely directed, so this is not an action-reaction pair. Of course not. There is a net force on this element of string because of those two tensions. And at this point right now, especially the way it's drawn in the book, if you look in the book, you can see that there is a net tension up. That's why it's slowing down. As the wave is going this way, the particle, that little particle of mass is going down, but it's slowing down and will come to a rest because there's a net tension upwards like that. So we would like to use that observation and apply Newton's second law to this one little tiny element of mass on the string right there. Well, let's write down A. The acceleration in the y is easy to write down. If you've got an element of mass and it's accelerating, then the acceleration is just the second time derivative of the position, isn't it? Yes?
For the fact that the angle up is canceling it, for such like plateaus in the wave, such as the peaks and the crests, or the ridges, wouldn't that space cancel the amount sideways? Because that space
Sideways, yes.
has zero up.
Yes, but not, and at times zero up as well, but sideways always yes. Yes, but let me get a little bit further, and I think I'll answer your question in more detail in just a few seconds. Okay. Well, A and the Y is easy to describe, and notice this, I'm sure you've seen this before, d squared y dt squared. The second time derivative of the position equation gives you acceleration. What's the funny d?
No, partial.
Partial, yes. And what does it mean when you say partial derivative?
Keep it constant.
Hold everything else constant, right? You're differentiating only with respect to time, and everything else is assumed to be constant. Which in a way you can buy that because we're going to be stuck at one particular x position, right? We're studying one particle and one particle only. So we're not moving sideways on the x, we're only allowing time to run forward. So this is the second partial derivative of y with respect to t. That's acceleration, and that is basically a definition of acceleration, isn't it? Now what about the mass? We're going to need that in Newton's second law. Mass, oops, let me write mass first. I'll go back to the answer. So what is the mass? It's going to be mu dx. Since the amplitude is small, dx approximates the length of the green segment. We've emphasized things here. We've made the waveform much more radical than is real. You know that if you pluck a guitar string, the guitar string does not vary much from the neutral position. So for us, dx is an approximation of dl because dy is going to be quite minuscule. Hence, therefore, the mass of the element can be approximated quite nicely as mu, the linear mass density, times dx, approximately the same as dl. Now, what about force? Force is going to be another story because force is, of course, directly related to the tension, but it's also related to the change in the slope at any given point. The slope here as compared to the slope here. Not the slope itself, but the change in the slope as we move across. So as you recall, the slope is the first position derivative. Let me just put this dy dx. But for us, we want not the slope, the change in slope, so it's going to be dy squared dx squared. So it's the first position derivative of slope. That's the rate of change of slope along dx. And that's all we're interested in because we're stuck on this one little element here. Just along dx, that's all we care about. And there's going to be some constant of proportionality right now. I'm just going to put a c there. And then I'll show you in just a moment that c is dx.
Is the t on there, is that tension or time?
This t is tension. I'm glad she asked that. Did everybody pay attention to that? That's tension in the string. So now we can write F equals ma. C t d squared y dx squared equals mu dx d squared y dt squared. Now we have the equation. I will assert once again and prove to you later that c is dx. The constant of proportionality is simply going to be dx. And if so, then you see immediately dx t d squared y dx squared equals mu dx d squared y dt squared. That immediately you can see that the dx drops out. And I'd like to solve this thing. I want to put the time derivative out front. So d squared y dt squared is equal to t over mu d squared y dx squared. And as you recall, this was assumed to be v squared. So, if that is so, now quite simply, d squared y t squared equals v squared times d squared y dx squared. And here we have it. That is the wave equation. Da-da-da. Isn't that just lovely? I'm so happy I can hardly stand myself. We have the wave equation. Now you guys, some of you at least, are in the differential equations class. Some of you have taken the differential equation class. Yes, this is just a second order partial differential equation in terms of x and t. And as you know, in your differential equations class, what they would ask you to do is to try to find a function y which satisfies the equation. In this class, we're not going to be quite so elegant about it all. What I'm going to do is I'm going to offer you equations. I'm going to offer you wave functions and ask you, do they satisfy the equation? So you're not going to have to make up the wave function. You're just going to test the wave function. Now, before we do, I would like to verify the assertion that was made, two of them actually, here and here, these two assertions, before I ask you to actually use this equation. I have to verify what I said. So let's go about the business of doing that, and our author does a lovely job of it. I really like his version of the proof, so we're going to follow him along very, very nicely, and I think his appears on the next page. Yeah, it does. And it's on page 506 in the light gray box, derivation of the wave equation for a string. And we're not going to do the same thing. However, let's emphasize the assumptions that we're making, because for this to be true, it's really got to be understood that, number one, that the weight of the string is negligible compared to the tension. Now, these two tensions in red here are significantly bigger than the weight of this piece of string. That's easy to accept if you're thinking about a guitar string, huh? The tension in a guitar string is huge compared to what the linear mass density is of the string. So that's the first. The second assumption is that the angles will always be small. Again, thinking about the guitar string, if you pluck the guitar string, if you think about the waveform that actually appears, y, x, probably the wave varies very little like that, very little. Hence, therefore, if that wave is very, very small, then these angles, theta, are never large at all. So two things very important. Linear mass density is small compared to t, and theta is always small. Go ahead.
That diagram you just drew, you're talking about like the actual cross-section of the string, is that a snapshot, or?
An actual snapshot of the string when plucked.
Yeah.
Yeah, that's what I'm talking
Not
about.
like the waveform.
Yeah, the waveform on that string is not doing this. It's doing this. That's all I'm saying. You got that on film. All right. Now, having made those two assumptions, let's now look at the force from the two x components. Okay, if we're looking at the string, and we're going to look at the two x components, the force horizontal from this tension and the force horizontal from this tension, of course, the way you do that is as follows. The net force in the x direction is going to be, well, in the positive direction, it is t times the cosine of that angle. So t is the hypotenuse. We have t cosine of theta plus d theta. And then in the opposite direction, it's a very similar, pulling backwards, pulling in the negative direction, is, here's the hypotenuse again, is t, the same t, and it's just the cosine of theta. So it's minus t cosine theta. There's the net force in the x direction. However, we just argued that theta small. So,
That D's tension, right?
t is tension, yes. So theta plus d theta is also small. So cosine theta is approximately cosine of theta plus d theta is approximately 1. Hence, therefore, f in the x is 0. Well, wait a minute, I thought it was accelerating. It is, just not in the x direction. The particles are only moving in the vertical direction, so we just verified, yes, there is no movement in the x direction. There's no net force in the x direction because the angle is small. But let's now look at the y direction. What about f in the y direction? Well, there are two forces in the y direction, there's a downward force here, and there's an upward force here. So if we look at what's going on from the left-hand side, we see that f and the y from the left, is going to be downwards minus t sine of theta, minus t sine theta. And from the right-hand side, if we're looking at this little element on the right-hand side, the force is now up. A very similar equation, f and the y from the right, is going to be plus t sine theta plus d theta. But again, theta, small, so sine theta is approximately tangent theta, which is dy dx. So now our net force in the y, F in the y, not from the left or the right, but combined, becomes equal to T dy dx at x plus dx minus T dy dx at x. So now we have two slightly different positions to deal with because we're dealing with a sine dy dx at the further position as opposed to the initial position like that. So factoring out the t because it's the same, we have t dy dx x plus dx minus dy dx at x like this. And lo and behold, you'll notice, what does it say? Look at Appendix A4. In Appendix A4, or your very good memory gives you that df dx is equal to the limit as dx goes to 0 of f of x plus dx minus f of x all over dx. The definition of a derivative. That's what we have right here, is the definition of a derivative. So that's in Appendix A4 if you didn't remember that, and I had to look at it to make sure I remembered it properly. So now we have the definition of the derivative right there. So what we have finally is that df in the y direction is simply t d by dx of the slope dy dx dx. In other words, it becomes t d squared y dx squared dx. Hence, therefore, we've just verified c equals dx. Aren't you happy? You're not looking happy. We just verified that. Okay. And that allows us then to complete our wave equation. And we have one assertion left. And that is t over mu actually b squared? Question mark. That's the next question we have to answer. And I think we can do that because we have an in-class problem. You get to do it. Not me. You do. I knew you couldn't wait for that.